Welcome to this session of our course. And in the last class, we have defined the partial differential equation. We have looked into the various types of equations: linear, non-linear, homogeneous, non-homogeneous, order of equation, and we have looked into detail the different types of boundary conditions one will encounter. Now, in this class, we will be looking into the classification, how we will be doing the classification or categorization of the partial differential equations. Now, let us look into the classification of equations. In most of the engineering applications, one will be dealing with the three independent variables. X1, X2 and X3. Now, typically we will be dealing with the second order equations in most of the cases. So, that can be written in general as summation of I is equal to 1 to 3, summation of j is equal to 1 to 3 a I j del square u del x I del x j is equal to r x 1 x 2 x 3 del u del x 1 del u del x 2 del u del x 3 in general. So, all the second order equations can be represented in this particular form. Now, let us look into the let us write the details on the left hand side. What is that? Nothing but the coefficients. We expand the summation series and we will be writing down the all coefficients of order 2 terms. So, any partial differential that will be of order 2, that will be recast in this form, particular form, and one can just open up the summation on the left hand side and can get the all the terms containing the order 2. So, let us do that. So, if you do that, I just open out the left hand side of this equation. So, I is equal to 1 2 3. So, it will be a I 1 del square u del x I del x 1 plus a I 2 del square u del x I del x 2 plus a I 3 del square u del x I del x 3. Now, I open up. So, I opened up the first summation over j. Next, I will be opening up the first summation over I. If I do that, this will be a I 1 a 1 1 del square u del x 1 square plus a 1 2 del square u del x 1 del x 2 plus a 1 3 del square u del x 1 del x 3. Next term will be a 1 2 del square u del x 2 del x 1 plus a 2 2 del square u del x 2 square plus a 2 3 del square u del x 2 del x 3. The third term will be a 1 3 del square u del x 3 del x 1 plus a 3 2 del square u del x 3 del x 2 plus a 3 3 del square u del x 3 square. So, we open up both the summation terms over I and over j, and we have obtained the 9 terms. Now, 9 terms of order 2 of the partial differential equation. Now, let us write down the coefficient matrix of these 9 terms. If you write down the coefficient matrix, so A becomes the coefficient matrix. The coefficient matrix will be nothing but A 1 1 A12, A13, A21, A22, A23, A31, A32, A33. So, we formulate the coefficient matrix for various for different terms, that those will be appearing in the order 2 terms of the partial differential equation. Now, we will be evaluating the eigenvalues of this matrix, and by looking into the values and sign of the eigenvalues, we can classify the the partial differential equation we are dealing with. Now, if so, we evaluate the eigenvalues of the coefficient matrix A, evaluate eigenvalues of coefficient matrix A. Now, if all eigenvalues are positive or all eigenvalues are negative, then the partial differential equation we are dealing with is the elliptic partial differential equation. If some eigenvalues are positive and some are negative, that means there is a eigenvalues which are some mixture of positive and negative numbers. So, this is known as the hyperbolic partial differential equation. If at least one eigenvalue is 0, then it is called a parabolic. Then it is a parabolic. Okay. So, we will be by looking into the coefficient matrix of the order 2 terms in a 3 variable problem, we can get the we can get the coefficient matrix. By evaluating the eigenvalues of the coefficient matrix, we can come to know the and by looking into the sign of the eigenvalues and the their values, we can come to know about the nature of the partial differential equation we are dealing with. Now, we will be going through some of the examples in order to explain this further. So, the first example I will be taking about will be an equation like u del square u del x square plus del square u del y square plus del square u del z square is equal to 0. So, in this problem, x 1 is basically x, y 1 is basically y, x 2 is basically y, and x 3 is basically z in the nomenclature that we have utilized earlier. So, it is basically del square u del x 1 square plus del square u del x 2 square plus del square u del x 3 square equal to 0. So, if you now get the coefficient matrix, the coefficient matrix will be 1 0 0 0 1 0 0 0 1. So, if you really find out the eigenvalues of this problem of this matrix, the eigenvalues will be 1 1 1. So, all eigenvalues are positive, all values are positive, and we are talking about an elliptic partial differential equation. Okay. Next, we will be taking an example of let us say parabolic partial differential equation. That will be example 2. It will be del u del t is equal to del square u del x square plus del square u del y square. If you recast the equation in the form that we have already discussed earlier, then and then prepare the coefficient matrix, the coefficient matrix will be 1 0 0 0 1 0 0 0 0. So, therefore, the eigenvalues will be 0 1 1. Since one of the eigenvalues is 0, then we are dealing with a parabolic partial differential equation. So, this equation is a parabolic partial differential equation. Next example, we will be talking about a hyperbolic one. So, del square u del x square plus del square u del y square is equal to del square u del t square. So, in this equation again we have to recast in the form that we have already discussed, that we take all the second order term on the left hand side, rest of the terms on the right hand side, and then if we formulate the coefficient matrix, the coefficient matrix becomes 1 0 0 0 1 0 0 0 minus 1. So, now if you get the eigenvalues will be 1 1 and minus 1. So, we have landed into an hyperbolic partial differential equation. So, broadly these are the ways to evaluate the nature of the partial differential equation, and there is a simpler version of doing that as well. If we are talking about the two independent variables, if there are two independent variables which are quite also in common, two independent variables instead of three. In the earlier case, we have talked about a three-dimensional problem where we are dealing with the three independent variables. Now, in this particular problem, we are dealing with a two-dimensional problem where we are talking about two independent variables. Now, that will be the general form. General form will be a del square u del x square plus 2b del square u del x del y plus c del square u del y square is equal to f of u x, means del u del x del u del y u. Okay. So, any other terms. So, if we express it this way, the two variable problem, and then we will be computing b square minus ac. Okay. So, if b square minus ac is greater than 0, then we are talking about a hyperbolic partial differential equation. If b square minus ac is equal to 0, then we are talking about a parabolic partial differential equation. If b square minus ac is less than 0, then we will be talking about a elliptical partial differential equation. Now, sometimes you may not be having the constant coefficients, constant value coefficients there, numerical values like 1 2 3 like that. In sometimes there will be variables as well. So, in that case, how will we be defining the equations? So, that will be depending on the nature of the variable we are talking about. For example, if we have a equation del square u del x square plus x del square u del y square is equal to 0. In this case, a is equal to 1, c is equal to x, and b is equal to 0. So, we compute b square minus ac, and b square minus ac is minus x. So, now if x is positive, then we will be getting an elliptical partial differential equation, and if x is negative, then we will be getting the hyperbolic partial differential equation. Okay. So, there will be the various ways to, so these are the ways to define the, to categorize the partial differential equation in case of two independent variable problem. So, we have looked into the classification or categorization in 3-dimensional problem and 2-dimensional problem, which are quite common in the engineering applications. Okay. Next, what we will be doing, we will be defining some of the terms which will be quite important in our in formulating and solution of partial differential equation into the by separation of variable. For that, we have to define some of the term or develop some of the theorems which will be quite handy and useful for us. Then we will define the what is called a linear operator. This is very important. So, the linear operator is the operator. L is a linear operator if L of alpha u plus beta v is equal to alpha L u plus beta L v, where alpha, beta are two constants. Now, ddx, what is an example of linear operator? ddx is a linear operator, d square dx square is a linear operator, integration is a linear operator. For example, integration of let us say alpha u x dx, alpha u x plus beta v of x dx is nothing but alpha integral u x dx plus beta integral v x dx. So, for example, ddx of alpha u plus beta v is nothing but alpha du dx plus beta dv dx. So, if these are the cases, then these are called linear operator, and any linear operator can have a will obey the principle of linear superposition. What is the principle of linear superposition? So, linear operators obey principle of superposition. Okay. What is the principle of superposition? Suppose I am solving an ordinary differential equation which is non-homogeneous. D square u dx square is equal to x, let us say, and boundary conditions are also non-homogeneous. At x is equal to 0, u is equal to let us say 5, and at x is equal to 1, u is equal to 10. So, this equation is equivalent to, if I break down this problem into 3 sub problems keeping one non-homogeneity in type. So, let us find out how many non-homogeneities are there. There are 3 sources of non-homogeneity are present in this equation, in this system. System includes the governing equation as well as the boundary conditions. So, there are 3 sources of non-homogeneities are present in this system, and what we will be doing next, we will be break down this problem into 3 sub problems considering one non-homogeneity at a time, and then we will be adding up all the 3 solutions, and then we will be getting the final solution. That means, if there is a non-homogeneous set of system, then we have to identify the sources of non-homogeneity. Suppose there are 3 sources of non-homogeneity in this particular problem, we have to break down this problem into 3 sub problems, so that one non-homogeneity will be appearing in a particular problem. So, therefore, the solution of all the 3 sub problems will be giving you the actual solution. For example, I will be defining this problem, and the solution will be the linear superposition of all the sub problems. So, I will be from 1 to 3. So, this will be u1 plus u2 plus u3. So, what is the definition of u1? u1 will be nothing but d square u1 dx square is equal to 0. So, in this case I will be forcing the boundary condition, the forcing the non-homogeneity in the governing equation to vanish and one of the boundary condition to vanish. So, x equal to 0, u1 is equal to 0, at x is equal to 1, u1 is equal to 10. So, this is the definition of u1. So, only one non-homogeneity is kept intact and rest two are forced to be 0. So, what is u2? u2 will be d square u2 dx square will be equal to 0. At x is equal to 0, u2 is equal to 5, and at x is equal to 1, u2 is equal to 0. So, in this case I am forcing the non-homogeneous term in the governing equation to vanish and the boundary at x is equal to 1 to vanish, keeping the non-homogeneity at x is equal to 0. Similarly, u3 will be what? D square u3 dx square will be equal to x, and I will be forcing the other two non-homogeneous and the boundary conditions to vanish. So, x is equal to 0, u3 is equal to 0, and x is equal to 1, u3 is equal to 0. So, in this case I am keeping the non-homogeneity in the governing equation intact, forcing the non-homogeneity on the boundary conditions. So, we will be solving, if you solve individually each of these sub problems. So, this is my first sub problem, this is my second sub problem, this is my third sub problem. If I get a solution of these sub problems individually and then add up the solution all in linearly. So, that means if we linearly superpose the solution of each sub problem, we will be getting the complete solution. So, just take this as an assignment and solve directly this equation with this boundary condition and check whether that solution is coming equal or not by solving these three sub problems one at a time and then adding them up by doing a linear superposition. So, that you can take that as an assignment and complete this problem and check that whether principle of linear superposition is valid for in case of an ordinary differential equation. Next, actually why this is important? This will be important because we will be quite often we will be utilizing this type of solution in case of partial differential equation, and we will be extending this for the partial differential equation as you go down along the our course. So, this will be very important principle. If the operator is linear, the operator the linear operator always satisfies the principle of linear superposition. Okay. Next, we will be looking into a set of equations. So, for example, I will be talking about if we extend the principle of linear superposition in case of partial differential equation. Let us see, let us give an example how one can go ahead with it. For example, if I have a partial differential equation like this, del u del t is equal to del square u del x square at t is equal to 0, u is equal to let us say 1 at for every x, at x is equal to 0, u is equal to 2, at x is equal to 1, u is equal to 3. So, if this is the case, then how will you break down this problem? So, there are three sources of non-homogeneities in this governing equation. In this system, the non-homogeneity is appearing at initial condition, non-homogeneities are appearing in the boundary conditions as well. So, how this problem will be solved? This problem will be divided into three sub problems considering one non-homogeneity at a time. For example, u will be divided into u1 plus u2 plus u3. So, let us look into the definition of u1. u1 will be del u1 del t is equal to del square u1 del x square, and boundary conditions are at t is equal to 0, my u is equal to 1, at x is equal to 0, and at x is equal to 1, I force the non-homogeneities to vanish. So, this is a non-zero initial condition, And what is the definition of U2? U2 will be del U2 del t is equal to del square U2 del x square at t is equal to 0. I put u is equal to 0, at x is equal to 0, put this u1, this u1. So, this u2 is equal to 2, and at x is equal to 1, u2 is equal to 0. So, I force the other two non-homogeneous to vanish, and I keep this non-homogeneity intact. So, that is the definition of U2. And what is U3? U3 will be nothing but del U3 del t is equal to del square U3 del x square. And what are the boundary and initial conditions? At t is equal to 0, my U3 is equal to 0, at x is equal to 0, my U3 is equal to 0, and at x is equal to 1, my U3 is equal to 3. So, here I force these two non-homogeneous to vanish, I keep this non-homogeneity intact. So, what essentially we have done, we have divided the problem into 3 sub problems, and we have seen that this how this sub, and it is easier to solve each such sub problems, and by using the principle of linear superposition we can get the complete solution by adding up all the solution of sub problem. And why this can be done? This can be done because our operator, what is the operator here? Our operator is del del t minus del square del x square. This is known as a parabolic operator, and this operator is linear. Okay. Now, let us look into the nature of the sub problem as well. If you have a partial differential equation where the initial condition is non-zero and the boundary conditions are homogeneous, initial condition is non-homogeneous and boundary conditions are homogeneous, then it is known as a well posed problem. On the other hand, if you have a partial differential equation, let us say parabolic partial differential equation with a homogeneous initial condition and non-zero boundary conditions. For example, you have the homogeneous initial condition and one of the boundary condition is non-homogeneous, then this is known as the ill-posed problem. Okay. So, similarly, the U3 is also an ill-posed problem because the initial condition is homogeneous. So, homogeneous, non-homogeneous initial condition and homogeneous boundary conditions are generally called well posed problem. And zero or homogeneous initial condition and non-homogeneous boundary conditions are known as the ill-posed problem. Okay. Why they are called? In case of well-posed problem, we can have a directly separation of variable type of solution, as will be seen later on in our course. In case of ill-posed problem, we cannot do that because the final constant that has to be evaluated in case of separation of variable will become 0 in that case. So, what is the solution? The solution is how to convert an ill-posed problem into an well-posed problem. So, I will stop in this class. In the next class, again we will be coming back, reverting back to this problem, and we will be seeing how an ill-posed problem is converted to an well-posed problem, and then we will be going ahead with the separation of variable of type of solution. Thank you very much.